Okay, assalamu alaikum everyone, and welcome to another session. Actually, I'm a little bit late today because our industrial training or industrial attachment has been going on, and I'm the coordinator over there also. So the session just stopped, just ended actually, one session, and I had to complete the formalities. Okay, so sorry for that. Okay, so let's continue with the modeling part that we did in the last class. That actually would help us to represent the mechanical power variable PM, which was basically an input variable earlier on. That means before we considered this hydroturbine dynamic model. Okay, so before we introduce this model or these dynamics into our system, we had something like this: omega dot, that is the nonlinear model, of course, and the linear one would be like this: omega base del omega dot was 1 upon twice h del PM minus del PE del EQ prime dot TDO dash delta EFD minus delta EQ. And the fourth variable, state variable, was the excited dynamics del V ref minus del VT. So these were the four state variables. And in that model, up to this point, we actually considered two input variables in the form of del PM and del VREF. But once we did it in the last class, this specific one, so we can clearly see that we have the fifth state variable arriving here in the form of del PM. So in continuation with this, if we include the hydroturbine dynamic model along with the fourth order model, where the first three belong to the synchronous generator up to this point, and the fourth one is the exciter. So this is SG up to this point, this is exciter, and this is turbine. So these are SG states. So these are the 5 state variables. But the problem is that if you remember, when we discussed the definition of state space model, it was something of this form. So it was like x dot, I mean the nonlinear form, if we start like that, x dot equals function of x and u. Okay. So what it meant is the x is the vector of a state variable on the left hand side of the state space model. So this is the state space model. So on the left hand side, we should have some vectors and their derivatives, time derivatives actually, okay, derivatives of the state variables. So on the left hand side of the expression. On the right hand side, however, we will be having all the algebraic expressions, okay, only algebraic expressions. There is no dynamics, there is no d by dt on the right hand side. So this was the nonlinear model, the nonlinear one. The linear counterpart was something like this. It was like x dot equals ax plus bu. Similarly, similar to this, we can say that on the right or left hand side, we have the presence of the d by dt operator. However, on the right hand side, we don't have any d by dt operator. So unlike this model, what we find here, that in the turbine state equation, we have the presence of a d by dt operation on the right hand side. So although this is a state equation, we can say this is one form of state variable representation, but we cannot directly include this model, this equation, fifth equation, into a state space model, okay, because of the presence of this d by dt of del g. What was del g? Anyone? What was meant by del g? Can anyone answer this? No one? What was del G? Okay, what was del H? Everything lost? Let me see who are here. Well, there are 10 participants. Only I am speaking. Okay, Rahid, are you there?
Yes, sir.
Okay, I thought I am the only person here. Didza, are you listening? Didza. Anas, are you there?
Yes, sir.
Okay. Can you recall what was del H? Just in short, I mean, yes or no? No, no problem, no problem, no problem. Can you recall any of the symbols, Anas? Del H, del U, or del G?
Last classটা ইয়ে করা হয়নি আসলে।
Okay, you couldn't attend. Okay, no problem. Ashif,
Sorry, yes, sir.
yes, can you tell what is del G or del U or del H?
As far as I remember, Del G was the gate opening.
It was the
Uh,
gate position. Excellent.
was-
It was the gate position. Okay. Change in gate position. Once we say del, it means the change in G. G itself is the gate position, gate valve. Excellent. Opening of the gate valve means what? If we open the gate valve, it will allow more water to flow to the turbine. Okay. So there's a turbine blades, the turbine shaft, and there is the gate. There should be a gate here. It's nothing but a valve. Nothing but a valve. So if this is the valve, then these two part of the valves are touched to each other, means your G is how much? How much is G in this case? If this path is closed, how much is G?
Zero.
G is 0. Excellent. That means you are not allowing any water to pass through the turbine blades. So how much will be the power output, mechanical power output from the turbine? This is the kinetic energy from the water. And this is the mechanical energy or mechanical counterpart of power, PM. So if G is 0, how much kinetic energy of water will be associated with this? All the waters are blocked, right? Cannot flow. Let's say this is the penstock. The water is flowing through the penstock and all the other elements. This is the dam. This is the head, etc. There is an opening. There is an opening, which is controlled by the sluice gate. Can you recall now? There's a sluice gate, which can be controlled at this starting point. So the water intake at this point can be controlled with the sluice gate. Water intake or water flow to the turbine blades can be controlled by this gate valve or G, position of G. Position of gate is G. So if G is 0, means the valve is closed completely. If G is 1, means it is completely opened. So G was the gate position of the gate valve, opening or closing. What is del U? Okay, what is del H? Generally, why do we use H, the term H? It was the water head. Okay, water head, change in water head. So these were the associated some of the variables that we used. Ultimately, we didn't actually use U. We got out of the representation of U term from we took out the U from our representation from this equation ultimately. So the final equation was actually a transfer function between the gate position or change in gate position and the change in mechanical power. Okay, so this was the relation. So now let's see what we can do actually with this unwanted term over here, d del g by dt. Del g by dt, this is not what we want. We want to erase it in a manner such that we only have some algebraic expression instead of this. So our target next is to get something like this, d del g by dt equals to some function of some algebraic variables, some variables, of course. This could be state variable, this could be any other input variable, but this side should be algebraic. So this is our next target. So that means we are looking for some expression of deviation in g with respect to time. Okay. So in reality, how do you control this gate valve? Any idea? How do you control this gate valve? Whether it is a hydro turbine or it is a steam valve, how do you control the opening? Remember, del G is nothing but the opening and closing of this valve over here. This is del G, let's say. So how do you control this movement? Okay, how do you move it into the upper direction and move it into the lower direction so that you can have some non-zero G value over here? That means you have to have some mechanism. Okay, you have to have some mechanism over here which will allow you to have some control over this positioning of the gate. Okay, gate valve, the two parts of the gate valves. So before we go into the modeling, let's try to focus on the necessity of this change in position in G. Okay, why do you need to change it? Because you see, we are looking for some expression d del G by dt. That means we're looking for some expression which will allow us to know how much change in G is there with respect to time. But the question is, why do we need to change this G actually? What benefit would we get, or when do we actually want to change it? Why do we want to change it? That is clear. We want to change it because we want to replace it here. Okay, this is one way to say. Another way to say, well, if we can incorporate this del G, deviation in del G with respect to time in some manner, then we can actually control the amount of water intake that is going to the turbine blades. Okay, let's say this is the turbine blades. These are the turbine blades which will be rotating, of course, in a certain direction depending on the water heating direction. Okay, at which angle water is coming and hitting the blades, depending on that water direction, the blades will rotate. And this blade is actually connected to the generator, ultimately generator rotor part. So now, if we can control this water over here, that means in a sense we can say that we are controlling this del G position. And if we can achieve that, what we will get ultimately, we can have some sort of control on the amount of kinetic energy, which will be ultimately converted to some form of mechanical energy or mechanical power, PM. Is it clear? The energy flow from the water, it is the kinetic energy, it is coming out. You can control the kinetic energy through the use of the gate valve positioning. Once you get more kinetic energy, what will happen? More kinetic energy means the blades will start to rotate at a higher velocity. So that will give you more mechanical energy output from the turbine. So that means if you can ultimately, by controlling the gate valve over here, we are controlling in a sense the PM. Now the question is, why do you need this control over PM? Anyone? If no one answers, then again I will go from person to person. No problem. Okay, there is one additional participant. Lelin, Abdul Mukit, are you there? Lelin? No response. Atif,
Yes, sir. Yes, sir.
who is it?
Sir, Lelin, sir.
Okay, Lilin. Okay. Can you help us to say or to understand if we can control PM, what benefit can we get? Let's say we are controlling PM. I am saying I can increase PM by changing the water flow or changing the gate valve position. At the same time, I can reduce PM. So PM is a function of del G, let's say. PM is related to del G position. Now the question is, if I can control PM, what's the benefit? Or what is the harm if I cannot control PM? The
Actually, sir,
Yeah.
sir, sorry, sir. I mean, I am joined right now, so
No, this is nothing to do with joining late or early. This is a basic question. So don't bother about this diagram over here. Just tell me, with respect to a generator,
Yes, sir.
with respect to a generator, the input is mechanical, right?
Yes, sir.
The output is electrical.
Yes, sir.
So now, if the load demand changes, of course, the load demand is varying continuously, right?
Yes,
You are
sir.
switching on devices, someone else is switching off devices. Sometimes this switching on and off is for large devices. I mean, devices or loads having large capacity,
Yes, sir.
megawatt, in the megawatt range. Industries are getting closed in the evening. Some machineries are, closed. Okay. Some are turned off, some are turned on at the early part in the morning. So loads are continuously changing.
Yes, sir.
So if load is changing, what do you think? What should be the effect on your generation? Should it also change or not?
It would change, sir.
It should change. How do you change the generation? That is this PG is nothing but P electrical, okay? Output of the generator. So don't get confused. This is
Yes, sir.
PE. So if load is changing, you have to change the output electrical power.
Yes, sir.
Otherwise, what will happen?
Sir,
Your output
Yeah,
electrical power is what? Load plus loss, isn't it?
Yes, sir.
If you do not control PE with the change in PL, then whatever power you are generating will be lost. This is the problem. So as a power station owner, you don't want losses to be there, or you actually want to minimize the losses, okay?
Yes, sir.
Just to save money, economics is involved. So you want to control PE, right? PL
Yes,
you
sir.
cannot control.
Yes,
PL
sir, load.
it's from the consumer. You cannot say, well, you are a consumer, don't turn on your light, right? You can't tell that. Don't run on your fan, don't run your AC. Okay. You can't tell that.
Yes, sir.
So you can't control it. So the controlling has to be done at this end, at the generation end. The load end, you can't control it. I mean, directly you can control it. There are some other methods, like you can make peak hour billing and off peak hour billing, but that is different issue. We are not going there. We can control in a way by imposing penalty in many ways. Okay. Okay. So you have to have some control on PE. How do you
Yes.
control PE? Because this is the output of the generator. These are the three terminals from the generator.
Yes, sir.
So this is the output. So to control the output of the generator, what you have to control actually? What is at the input?
Sir,
I'm talking about
Water.
real power output. Yeah, actually, I don't go up to the water point of water. I'm just saying you have to control the prime mover torque.
Yes, sir.
Prime mover torque. Because the speed is there, synchronous speed. So you can play with the torque. So that torque is actually coming from this kinetic energy. Can you link up now?
Yes, sir.
Can you relate now what is going on?
Yes,
I
sir.
hope so. Okay. So in conclusion, because we cannot control the load directly, we have to control the output of the generator. And that is only possible by controlling the torque of the prime mover. So this is the conclusion. And that torque of the prime mover is actually dependent on, if it is a hydro turbine, hydro generation system, then this is controlled by del G. You get the point? So that means if we can have the dynamics of del G available, if we can model it, then we are done almost. So this job is done basically in real life by a device known as governor. Have you heard the name governor? It's not the political governor. It's the mechanical governor, or the governor that governs the power flow. Okay, controls the gate positioning of the generation systems, steam governor or hydro turbine governor, etc. Now, when will the governor start to act? This is the next question. When or how will it sense that it has to change this gate valve positioning? Okay, so that means the job of the governor will be to sense. So where is the change actually happening? At the starting point, where is the change? The change is occurring at the load end, right? At the load end, there is change. And to cater for that change, you have to change the PE. And that will be done by PM and through the governor gate valve positioning. So if you have, let's say PL is reduced, okay, load demand is changing, PE is fixed, then there will be some imbalance, isn't it? PE minus PL, generation and load imbalance. What will happen? What will be the effect? Anyone? We talked about one thing, that was PM minus PE. Now I'm talking about a little different thing, PE minus PL. I actually have I already have mentioned this. Okay, this is nothing special. Already I have mentioned. If you have PL getting changed, PE not changed, actually this parameter will be affected. Okay, loss will be affected. So you sense the load demand, you sense how much load is there, load variation is there, okay, demand is there. So you record the demand and you try to change your PE. Okay, so once you try to change your PE change is instantaneous. PE change could be done instantaneously. It is electrical quantity. PM cannot be changed instantaneously. It is a mechanical quantity. It comes out from the mechanical devices. So there will be some time gap, time difference. Okay, let's say PM is fixed and PE is reduced. Why PE getting reduced? Because PL has been reduced. Okay, so PE getting reduced, but PM, you have to reduce it to make a balance between these two. You have to reduce it, but it will take some time. What will happen in between? Let's say your P electrical requirement is nothing but 50 megawatt. Okay, PM was 50 megawatt. So I mean, of course, I'm ignoring any losses in between. So there was a balance between load and generation as well as the mechanical power input to the system. Now PE gets reduced to PL gets reduced 40. So how much you have to supply? 40. This cannot change instantaneously. This cannot change instantaneously. So what is the resultant power? PM minus PE. Where the effect will go? It is plus 10. Where the effect will
10
go?
megawatt will be loss.
Not loss. This is between PM and PE now. I'm not talking about PE and PL. That part is done. I'm saying that, well, PE has to be 40. Okay, PE has to be 40 because the load demand has changed. So what will happen to this 10 megawatt? What it will do? Remember the swing equation? What is this? Okay, let's take it without incremental variable. PM minus P. Now tell me what will happen. Okay, what is the speed when both are 50? What should be the speed? Synchronous speed, isn't it?
Yes.
Okay. So once there is imbalance between PM and PE, so let's say PE is getting reduced. Actually, load is getting reduced. Load is getting reduced. So that is translated as PE. Now, PM, you have to change to again bring balance between these two. But before the balance is established, there will be some imbalance. It will take some time. Okay. So what will happen in between to the speed? Will it remain at synchronous speed? Let's say the speed was 1500 RPM. So what will be omega now? I don't want the exact value, just what will happen to omega? This is my question.
Omega will be reduced
Omega will be reduced. Why? Why do you think so? What is the explanation, please?
because we need less output power. So the input power
We
should
need less output power, okay? But if I look at the expression itself, what does it say? Does it follow your logic? This is plus, this is minus, okay? How much is the resultant?
10.
10. Let's say H is whatever, 1 or 2 or whatever. It is a constant, okay? It will not change. So what is happening to omega dot? Is it positive or negative?
Positive.
Positive. What does it mean? The omega dot means this, right? Positive means it will increase. Now tell me.
Yes, sir. The change of velocity is increasing.
A change of velocity is increasing. So it should increase from 1500 RPM to some higher value, right?
Yes, sir.
Are you getting it? This
Yes,
is
sir.
important. What topic? The topic that I will discuss next, this part is very important to understand. So a change in load actually can be sensed quite easily by the change in speed of the system. By system, I mean the change in the speed of the shaft. Okay, this omega is nothing but the rotor speed, right? Rotor shaft speed. And you can easily monitor this value. You can easily record this value, track this value, monitor this value, whatever you want. Tachometer. Okay. So if the load decreases, that means the PE decreases, the PM cannot decrease instantaneously. It is set at some initial value of 50, let's say. The resultant thing, what it does, it actually affects the speed in such a way that the speed increases from synchronous. So this speed would be sensed. Okay, let's say it becomes 1550. The speed changed and became 1550. What should be your reference speed? Let's say if I talk about some control mechanism, what should be your omega ref? In general, reference value means the value at which I want the variable to be fixed. Okay, now tell me, what should be the reference speed for a synchronous machine? In general, I'm not asking for the numeric value. In general, for a synchronous
speed.
Excellent. So I'm asking about the generic form, generic result. So it should be omega synchronous. Okay with everyone? So the reference value should be omega synchronous. Is it okay? Because it is synchronous machine, so the speed should be synchronous, irrespective of whatever happens to the load. Ultimately, once the system settles, it should settle back to synchronous speed after the disturbance period. Now, however, the actual value of omega has increased. So this was 1500, this should be 1500, and this became how much? 1550. Why? Because reduction in the load, reduction in the power output demand. So this is a summing junction. This is a summing junction, and this is the error in speed. So we need to have some control mechanism, some controller which will actually drive the plant and which will take care of this error, okay? And that controller is nothing but the governor. In short, I am writing it as gov, okay? Just to save some space. The governor would do what? The governor would drive the gate valve, right? The governor would control the gate valve position, G. Governor would give me some different G. Okay, let me make it in terms of the variables that we have used. So governor would give me some change in G. Based on what? Based on whatever error I have here, omega error. Okay. Governor would sense this error. Then accordingly, it will provide some del G. What the del G would do? Now tell me what the del G would do. If del G changes, what will change? Quickly, time is running.
Valve position.
Okay, then what will happen? Del G means valve position. Excellent. What will happen? Physically, what will change then? More water
Total
will
speed.
flow. Yeah, more water will flow. So kinetic energy, right? Kinetic energy. This kinetic energy will run. This kinetic energy will run what? The turbine. So ultimately, I can skip this. I will get kinetic energy, but the device is not kinetic energy. Device is the turbine, right? Turbine. What the turbine will do, it is connected to the generator shaft. It will run the generator accordingly as per requirement. Now there is a sensor. This sensor would give you the speed. This is the closed loop. Are you getting the point? This is the actual speed value being sensed and fed back to the governor control circuitry. Any question about this block diagram? You can ask. If you don't ask, and if you have confusion, then there will be problem. Because we'll be moving into the mechanism now. And I'll be referring to this diagram probably every time. Any question? No question. Everyone understands everything. That's not possible actually in reality, but however, this is possible in my class. I don't know how. Okay, so let's continue. So we have seen that the governor is actually nothing but, we can say in a sense, it is something like a control mechanism which controls the gate valve position, right? It controls the gate valve position. And we want the block diagram representation of this today. This is our target. So now let's see how we are going to achieve that target. This is already done. And whatever I have said till now, these are the summary of these 3 lines, actually, you can say. In the summarized form, these are the 3 lines that I have drawn and I have mentioned for you. So there are some, of course, different types, and along with time, the type of governor mechanism has also evolved from the very old type to some modern types, of course. We'll be taking one of the examples, and that is nothing but known as the fly ball type governor mechanism. In other words, it is the mechanical type governor, but in today's world, in modern power systems, they probably will not go for the mechanical type. They will go for some electrical type. But for understanding the mechanism, we can start from the mechanical type governor. Okay, if the concept is clear for mechanical type governor, then actually the actuators may be replaced, but the working mechanism would be almost identical. Okay, the actuators would be replaced, nothing else. Okay, so now let's move forward. So our target next is to understand the working mechanism of the fly ball governor. So let's see the diagram first, the schematic diagram, one which is shown here. Okay. So let's go through the parts first. The first part that we are seeing here is nothing but a reference setter. And this reference is nothing but the speed reference setter, speed set point. Remember I talked about omega ref, right? So the omega ref could be settled by, or could be changed by this speed set point. If I move these, element towards the top, then my speed set point would be lowered. And if I do the reverse, that means the pointer is moved towards the lower direction, then the speed set point would be raised. How would it be possible? We will explain it later on. Okay, so if I move the pointer up, I will have a lower speed set point. If I move this pointer down, then I would actually have a raised speed set point. This is the summary. Okay, then I have two arms actually. So ABC is one of the arms, or one of the connecting rods, which is being pivoted at point B. Okay, what is the meaning of pivot? Means if point B is fixed, then if arm A goes down or arm A goes up, then actually this is point B. Considering point B is fixed, then if point A goes down, this is point A. If this goes down, then point C should go up. Okay, that means if you press it down, because it is being pivoted here, it is being fixed here. Point B is being fixed, the arm is being fixed here at this point. So if the left side of the connection, that means rod AB, if this goes down due to some pressure or due to some force being applied on it, then the arm BC, the point C, would go up, and vice versa. This is the case if point B remains fixed. So in summary, if B is fixed, because it is a pivot point, let's say take it as point number 1. If B is fixed, then if A goes down, then C goes up, and vice versa. Clear? Vice versa means simply if A goes up and then C goes down. Now, if point B itself moves up or down, then what will happen? Considering no other force is being applied on A or C. If point B itself moves up and down, and B being a pivot point for the arm ABC, then what will happen to A and C? So if case for, let's say point number 2, if B goes up and there are no forces being applied on A and C, no external force is being applied, then what will happen to A and C? Okay, let's say if B goes up, that means the whole body then will go up along with it. The whole body will move. Okay, the whole part will move up, and vice versa. So A and C both goes down. Point number C, or sorry, point number 3. Now, if on the other hand, well, B is pivot point, no problem, but A is somehow it is fixed. Okay, if we fix A, then B goes up. What will happen to C? A is fixed. A is not moving, but B goes up. What will happen to C? Will it remain fixed or will it move?
I think it would move.
In which direction?
It would follow the B direction.
It would follow B direction because B is the pivot point. Okay. B will take C along with it, considering A is fixed. Excellent. Now, if this is the reverse case happens, again, if A is fixed somehow, let's say A is fixed, and we are moving B downwards. So point C would be taken along with B. Okay, considering point A is fixed. So these are some of the points associated with the movement of the arm. Okay, I have discussed a few of the cases. First case was if B is fixed, then if you pull A up in the upwards direction, sorry, if you pull it down, okay, if you pull A down according to this direction, according to this sign, then C should go up. This was case 1, the figure actually I have erased. This was for case 2. If B goes up and neither A nor C is fixed, then both should go up along with B. However, if A is fixed, then if I pull B downwards, C would be also coming downwards. Okay. So these are some of the observation for arm A, B, C. Why we are talking about point A being fixed? Because we can see that there is a connection between point A and this element, the reference setter. Okay. If I do not change the reference setter, then point A is unmoved. Remember, okay. If I do not change the reference setter here, if I do not pull it up or push it down, then position of A is not going to be changed. The position of A is only going to be changed once I touch this set point. Okay. So these are some of the observation or some of the comments associated with the arm ABC. So similarly, CDE is another arm. CDE is another arm which is pivoted at point D. Okay, and similar observations, similar comments are applicable for CDE, where actually we can see that there is no other element connected to C. However, with point B, there is the fly ball mechanism. This is the fly ball mechanism. How does it work? Let us see. So there is a spring which is connecting the two fly balls. Okay, there is a spring which is connecting the two fly balls. This is one of the fly balls. This is another fly ball. And the lower part of this rod, this vertical rod, the lower part of this vertical rod is fixed. That means it will not move up or down. It will not move in the vertical direction. However, it can rotate. It can rotate along its axis. Okay, it can rotate along its axis. However, it cannot move up and down. The upward or downward vertical movement, vertical bodily movement is not possible, but the circular movement is possible. Am I clear? The circular motion is possible. The linear motion vertically up and down is not possible because of this fixed point here. Is it clear?
Yes.
Okay. So now if you can remember what I just said before in the previous slide, that the speed would be sensed, right? The speed would be sensed. 1550 RPM, speed getting increased. That should be sensed from the generator shaft. So this is the shaft speed. Okay. There's additional mechanism which is not shown here. So that would be transferred to the rotation, the energy, this additional energy here, the extra energy would be transferred to this lower connecting rod here. if the speed increases from 1500 rpm, at steady state, speed should be 1500 rpm. When the speed increases, when actually will the speed increase? If PL reduces, right? PL reduces, PM minus PE becomes positive. If PL reduces from a certain operating point, then PM minus PE increases. That is translated as the enhancement or the increment in omega from omega synchronous. That would be sensed here. Okay, that would be sensed here. So once this shaft runs at a higher speed, what will happen here? If the shaft runs at a higher speed, the spring will expand. Okay, the spring, the fly ball will move apart because of the higher rotation here. Because of the higher rotational speed, this spring tension, whatever spring tension was there, due to the high rotation, now the rotational motion will exert more pressure on the spring. So the spring cannot sustain its, whatever position was there for the spring. So it will expand itself due to the extra additional force of 1550, additional 50 RPM. So the spring tension will be relaxed. The fly ball will move apart. Are you with me, or should I repeat?
Sir, can you please repeat?
No problem. I can repeat. Let's start again. No problem. Okay. So let's say now at this point, of course, there is a certain distance between these two fly balls, right? Isn't it? At a certain point of operation, there is a certain distance between the two fly balls, and that is associated with the spring tension. Okay, the spring is pulling them together, okay, trying to pull them together closer, right? This is the job of the spring. You just hang a spring. What it will try to do, it will exert a pressure towards its center, isn't it? Let's say this is a spring.
Yes, sir.
So what it will do, you just fix these 2 points. You will feel that a pressure is towards its center, not away from its center, right? This is due to the spring tension. We call it spring tension or the spring force. It will try to pull the 2 ends together. This is the job of the spring. So, but however, there is a certain shaft speed. Let's say the shaft speed, let's say the position here is S1 and S2. Okay, these are the 2 ends of the spring, S1 and S2. These are the 2 ends. Now, why these 2 balls are not coming together or closer? These are just not nails. Okay, we are not putting the nails on the 2 ends of the spring and putting it on the wall. Okay, it's not like that. If you put 2 nails on the wall, then of course the spring will be hung like that, right? Just put 2 nails, just hammer down 2 nails at the 2 ends of the spring. You can put the spring on the wall or some fixed body. But I'm not fixing this. Instead,
It's rotating.
yeah, it's rotating. The spring is not rotating. This shaft is rotating. I'm coming to that later on. I'm just talking about this distance now. This distance now. So this is the spring, and these are the balls, fly balls. Okay. So the spring tension trying to pull the 2 balls near to its center. Is it clear? These are the 2 balls. Due to the spring tension, the balls will experience a force towards the center of the spring. Is it clear?
Yes, sir.
Very good. But why they are not actually coming close to each other? Let's see. So that means there should be some other force which is acting in the reverse direction, isn't it? Some other force which are pulling the spring in the reverse direction, in this direction. So what is that force? That force is this centrifugal force due to the shaft speed. Now is it clear? So this force, the outward force, is due to the centrifugal force. Let's say we call it Fc. Okay, Fc is away from the spring. And F spring is trying to pull, Fs is the spring tension, is trying to pull the balls together. The shaft speed, as the shaft is moving here, it is moving, so it is creating a centrifugal force on the spring. And there is a balance, Fc equals to Fs. At steady state operation, not always, at steady state operation, means when omega equals to omega synchronous. So due to the rotation over here, the spindle, this spindle is moving, the rod is moving over here, and that movement is creating some centrifugal force which is keeping the balls apart, keeping the ball distant apart. However, there is a force due to the spring tension which is trying to keep the balls together, and there is a balance between these two forces. This is the centrifugal force due to the shaft speed, shaft rotation, and this is the spring tension. Is it okay now?
Yes, sir.
So there are actually two opposing forces acting on the spring. This is the summary of all the discussion that I have made. Two opposing forces. One is due to the spring tension, which is trying to pull the balls together. Another one is the change in shaft speed, or the shaft speed itself, which is being sensed by a sensing mechanism, which is not shown here actually, but there is a sensing mechanism. And depending on that actual speed of the shaft, that is omega, this lower spindle or the lower rod will change its rotational speed. And accordingly, the centrifugal force on the spring will change. Is it okay now? I hope so.
Yes, sir.
Okay. So at a steady state, there will be balance. There's no question about that. There will be balance. And due to this balance, a certain distance will be maintained. Let's say that distance is, so at a steady state, the distance is S1, S2. Let's say this is 10 meter, or let's say 10, whatever, centimeter, something, any unit you use, okay? Let's say 10 centimeter. Don't go after the value. This is just arbitrary value, okay? 10 centimeter, and don't go after the unit also, just arbitrary value, S1, S2. So now, when this speed, this shaft speed increases, which force will increase here? Which of the two forces should increase? If this shaft speed increases,
Fc.
Fc would increase. So what would happen to the spring? Will it extend or will it shrink?
It will
Extend.
shrink.
So you have two opposing opinions. Now you decide what will happen. Again, let me explain again. Fc is working in the outward direction, okay? It will try to pull the ball away. Remember, this is Fc. So let me draw here separately. This is Fc. Fs is this, due to the spring. Fc is due to this speed. Okay? So when it was omega equals to omega synchronous, this distance was 10 centimeter with the spring, center of the balls. So next I asked that if the shaft speed increases, which force would increase?
Fc.
Fc would increase. So now tell me, will the spring extend or shrink?
Will extend.
It will extend. Excellent. So in summary, if omega increases, we can relate it. That would be sensed by the shaft speed. We can relate it now with the positioning of the spring or the length of the spring. So the spring length S1, S2 would increase. Clear? Means this distance would increase because FC would become more than Fs. This is the reason. You got it?
Yes, sir.
Excellent. In the reverse scenario, if omega reduces, what will happen? Again, this balance will be disturbed, right? Again, this balance would be disturbed. Now, how will it affect the values of S1, S2? So if omega reduces, that means this rotational force will now have less effect, less centrifugal force being applied on this spring or the balls. So what would happen if there is less centrifugal force? The attract or the spring tension would go higher. Spring tension would go higher. So compared to 10 centimeter, of course, S1, S2 would decrease because the centrifugal force is now less than the spring tension. Clear?
Yes, sir.
Yes or no? Okay, yes. Thank you. So now, what's next? If this is understood, then we have covered a good portion. So now this is how the speed is sensed and the fly ball mechanism actually works. Now let's come to the position of point B. If this hard part is done, hard part is understood. Now tell me what will happen in this case to point B. Considering again, we are not touching point A. We are not changing the reference setting. Point A is fixed.
B will
point-
down.
So if S1, S2 increases, B will go down. Understood? If these two balls go apart, go away, this point is fixed. This cannot change. This cannot move up or down. This point is fixed. So of course, if these two balls move away, then a spring will extend itself and this point will go or come down. Is it okay?
Yes, sir.
B comes down. A is fixed. Excellent. So A is fixed, B comes down. Then what will happen to C? A is fixed, B comes down. What will happen to C? Quickly.
C will also come down.
C should also come down because B is the pivot point. C will come down. Excellent. Continue now. What will happen to D? Okay, for understanding D, we have to make sure that what is actually going on with this arm. Okay. Now let's explain what is actually happening here. CDE is another arm, as I said. As I just said, CDE is another arm where D is the pivot point. Okay. But like A, E is in some way, it is also connected to some other part of the system. Okay. E is not floating like C, right? It is not simply floating like C. C is a floating point. It is not connected to any other element of the system. However, E and D both are connected to some other part of the mechanism. D is connected to a piston valve. D is connected to, with the help of a connecting rod, of course, it is connected to a piston valve. Point E is connected to the main valve shaft. This is the shaft, which is ultimately connected to the main valve. This is the main valve. This is the piston valve. This is having a low power capacity, low power handling capacity. This is having a high power handling capacity. It's pretty easily, it can be pretty easily understood with the simply look at the thickness of the connecting rod here or the piston here. Okay, it's very thin. It can't actually pull up or pull down large amount of power. But this one, it can carry, it's a big shaft. Okay, like a hammer. You see the hammer head. is a big shaft compared to this piston valve shaft. This shaft is pretty large. So the movement over here, any movement over here is associated with high power transmission. And any movement over here is compared to low power transmission. And thus, we call this block over here as hydraulic amplifier. Okay, why it is an amplifier? Because simply it transmits or it transforms a low power input to a high power output. Thus it is an amplifier. Why it is hydraulic? Because the mechanism runs actually with the help of some fluid movement, some high pressure oil movement. How it actually works, we will discuss it inshallah detail in the next class, not today. But let me tell you that this is hydraulic amplifier because it works with the help of some high pressure oil movement through the chambers. In the next class, inshallah, I will say what is going on or what actually happens next with the movement of the high pressure oil, how it moves through the channels and how it actually moves the valve. But today, let me finish this topic, for the time being, by saying that this movement of the main valve actually closes or opens this gate. This is the gate or steam valve, gate valve or steam valve. Okay, this is the opening and closing of the gate. So you can see if this piston moves up, probably somewhere here, then is there any opening left? If this piston moves up, then this chamber gets closed, right? And no more entrance of steam is possible. No more admission of steam is possible. On the other hand, if this piston goes down, there are too many lines, let me erase. If this one goes down, then the opening becomes larger, right? So more steam can come, more steam can flow. If this goes down, more steam can go to the turbine. This is going to the turbine blades. So this is how, if we can somehow control this main valve movement, of course, with the help of this piston valve movement, then we will see that, well, we can control the steam flow. And once we are able to control the steam flow, that will enable us to control the mechanical power, PM. Okay. Any question? There is something left, still something left with the movement of C, D, and E. That would be taken in the next class, inshallah. Any other question? You never have questions. That's good. But the problem is, once I ask questions, you also remain silent. When I say any questions, you remain silent. So what does it mean? I know there are some persons who are teachers by profession. So I think they can answer it in a better way. So if your students or if your class participants are always remaining silent, what does it mean?